Hey everybody, this is the lecture for section 5.4, which is on triple integrals. So consider a rectangular box a less than or equal to b, or a less than or equal to x less than or equal to b, or let's call it this, a1 less than or equal to x less than or equal to a2, b1 less than or equal to y less than or equal to b2, c1 less than or equal to z less than or equal to c2. So that's a rectangular box. And how does it look in three-dimensional space? Well, here's A1 and A2 on the x-axis. Let's extend it into the xy plane as such. And then B1, B2 on the y-axis. And let's extend those into the xy plane. And look, I put that right where the z-axis is supposed to be. It's not what I wanted to do. So we'll put B1 here. And let's extend those upward in the z direction, these intersection points here. Straight upward. And on the z-axis, let us mark off C1 and C2. And up the top here is going to be where C2 is. And then C1, we'll just pick a spot. So here's the box. So we've got this box hanging out in space. And now suppose that we have a three-variable function in this space on the box. So we'll go this way. Now consider a three-variable function w equal to f x, y, z, or just f of x, y, z on B. And what should f represent? We can no longer talk just about volumes of geometric objects in three dimensions. We've gone beyond that now into, a function whose domain is three dimensions and whose range is one-dimensional. But we're not going to step into 4 dimensions and start talking about volumes in 4 dimensions, hypervolumes or whatever. Okay, consider a three-variable function on B. Think of f as a density function. As a point variable density function on B. So B is a solid object, and at every point there's a certain density, and that density varies. It's not uniformly dense, okay? And it's a continuous function. So that's probably the easiest intuition to use with this is the idea of a density function. Other things you might think of is f as maybe a temperature function. At any given point there's a different temperature. I think density is a good idea. So now let's define a integral, triple integral in 3 dimensions using f in the analogous fashion that we did in 2 dimensions. Let delta x equal a2 minus a1 over n, delta y equal b2 minus b1 over m, and delta z equals c2 minus c1 over l. Right, and xi is equal to a1 plus I delta x, yj is equal to b1 plus delta j delta y, and zk is equal to c1 plus k delta z. So we've cut up the interval on the x-axis, y-axis, and z-axis into subintervals of equal length. Okay, this subdivides B into small sub-blocks of volume delta V equal to delta X, delta Y, delta Z. All right, so the picture to think about here is as follows. Okay, so you've got your box, and it's all nicely subdivided on each coordinate axis. And what you've done is you've cut up the box into these small sub-boxes. Pretty bad, let's see. There we go. So this little box inside here looks like this. So the length across the bottom there is delta y. The depth across the bottom and the top or whatever is delta x. And the height there is delta z. So you have that delta v for volume is length times width times height. Okay, given the continuous function f, typically we want the function to be continuous. F, x, y, z, define the triple integral over b of f x, y, z, dv. Define it in the same way we've been defining it. Okay? How have we been defining these multiple integrals? Well, it's the limit as m, n, l go to infinity. Instead of double sum, we got a triple sum over I, j, k, f, x, I, y, j, z, k, delta, v. Same idea that we did before, right? With single variable functions, it's the limit of the sum over I, f, x, I, delta, x. With two variable functions, it was the limit of the sum over I and j, f, x, I, y, j, delta a. Right? Delta length, delta area. And here it's the limit of the triple sum f, x, y, z, delta v. Right? So you pick a sample point within this box, within these little boxes. So I'm picking the upper rear, I'm picking the upper left-hand front point. So within each little sub-box, my sample point is the one right here. Doesn't matter which, you just have some sample point within the box. Since the function f is continuous, okay, you think of f as being more or less constant on these small boxes. So you just take any sample point for f, and f is going to be about that value over the whole block, and you multiply it by the volume of those little blocks. What does this represent? I mean, it doesn't represent a volume anymore or an area anymore, right? The single variable integral represents an area. Single variable integral, it's this area here. The two variable integral, right, it represents the volume under the surface over the domain, of this thing here. But the three variable thing, no. Right, it's a four-dimensional hypervolume, whatever that means. Okay, but what can we think of? Thinking of f, what intuition can we use? Thinking of f, x, y, z as a density function, right, in units mass over units volume. Thinking of f as a density function, units mass over units volume. When f, x, y, z is continuous and delta v is very tiny, okay, f, x, y, z is more or less constant on any one tiny box, right? So f, x, I, y, j, z, k, delta v, this is units mass, also mass over volume, and this is volume, equals the mass of the small block. Right, it doesn't equal, it's approximately the mass of the small block. So, right, the triple sum I, j, k of the approximate mass of each block, when you add up each block, estimates the mass of the entire block B. That triple integral estimates the mass of the entire block B. So, and then the smaller delta V is, the better the estimation turns out to be. So the triple integral, which is the limit as delta v goes to 0, or as m, n, and l go to infinity, so this thing here equals, no longer estimates, but equals the mass of B with density function F. Right, so you got that variable density function, now you've got the mass. And you can even think of F having a negative value corresponding to a negative mass. I mean, it doesn't make sense physically, but, you know, in this intuition we got going here, it's just fine. So you have, you know, mass and anti-mass or something like that. Right, now you can do this in any dimension. I mean, in dimension 1, if you thought of a single variable function, you just have this kind of stick. You know, x equals a to x equals b, and then f of x is the density of the stick at a certain point, in which case the integral over the whole stick is the total mass. Or in a two-variable function, you've got some domain in the xy plane, and then fxy would be a density function in mass, units mass over units area at any given point in this domain, in which case the double integral of f over that domain represents mass. So instead of jumping up into a measurement of one dimension higher, you're getting a measurement that has no dimension, a mass measurement. Okay. All right. So that's what it means. Total mass. How does one calculate the triple integral? Well, over a box B, you calculate it in the same way that you do with double integrals. You iterate it. Okay. Calculating triple integral f x y z dv is again done by iteration. Okay, the explanation requires talking about mass instead of volume, but you know, we'll leave out the discussion. It works out in the same way as it does with double integrals. So triple integral over b f x y z dv is equal to, well, you have to pick in what order you're going to do. X first, dx, dy, dz. Right, so you do the antiderivative with regard to x, holding y and z constant. Then you do the integral with regard to y, holding z constant. And then you do the integral with respect to z. And at each step, that variable goes away. After the first step, the x goes away, and you're just left with y and z. After the second integration step, the y disappears, and you're left with just a function of z. And then at the end, you just get a number. So, I mean, you can do dx, dy, dz, or any of the, you know, other six, well, any one of the 6 ways. You can do the y first, b1, b2, c1, c2, a1, a2, f, x, y, z. So this is dy, dz, dx, you know, etc., etc., etc. There's 6 ways to do this. Dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, and what else? dz, dx, dy, dz, dy, dx. All right, 3 factorial equals 6 ways of ordering that integration. So let's do a quick example. Boxes are not like the most interesting objects to do triple integrals with. But we got to do an example, so let's do one. So let's calculate triple integral x squared plus yz dv over b for b equal to, so minus 1 to 1 for x, 0 less than or equal to y less than or equal to 2, and 1 less than or equal to z less than or equal to 2. And let's calculate this in two different ways. I'm not going to do all 6, obviously, but let's try two different ways of doing it. So let's do dx, dy, dz. So the x's go from minus 1 to 1, y is from 0 to 2, z is from 1 to 2, x squared plus yz dx, dy, dz. So first do the antiderivative with respect to x. So that's 1/3 x to the third plus yzx from x equals minus 1 to x equals 1 dy dz, right? We did the antiderivative with regard to x, holding y and z constant. Now we evaluate at 1 and negative 1, and we're going to get a double integral in terms of just y and z. So evaluating at 1, you get 1/3. Evaluating at negative 1, you get negative 1/3, but we're subtracting them, so you get 2/3. Here you get yz, negative yz, but we're subtracting them, so you get 2yz. dy dz. Antiderivative with respect to y, 2/3 y plus y squared z for y equals 0 to y equals 2. So at 2 you get 4/3 minus 0, and then here plus 4z minus 0 dz. So this is 4/3 z plus 2z squared from 1 to 2. So 4/3 times 2 minus 1 is 1, plus 2 times 4 minus 1 is 3, is 6. All right, so I've got 18/3 plus 4/3, 22/3. Okay, let's calculate it in another way. So let's do y first, and then x, and then z. So x squared x squared plus yz. And then this is dy dx dz. So antiderivative with respect to y, we've got x squared y plus 1/2 y squared z from y equals 0 to y equals 2 dx dz. So this becomes, so at 2 you have 2x squared, and then at 0 you get 0. At 2 you get 2z, and at 0 you get 0. dx dz. Antiderivative with regard to x, that's going to be 2/3 x to the third plus zx from -1 to 1, x equals -1 to x equals 1. So it's integral from 1 to 2. So at 1 you get 1, at -1 you get -1, or 2/3. But we're subtracting them, so those get added. So you get 4/3 plus 2z dz. I think that's the same one as last time. 4/3 plus 4z dz. So, right? (22/3). Same answer. As it should be, no matter how you do it, you're always going to get the same answer. Okay. All right. So that's blocks, but what sort of more general regions can we have? That we can do iterated integrals on. So with iterated integrals, how does it go? You do the first integral, integrate the first variable, holding the other two constant, right? So when you're doing dx, dy, dz, first you integrate with respect to x, holding y and z constant. Then you integrate with respect to y, holding z constant. And then you integrate with respect to z. So for each, the type of region that you could do this type of iterated integral on would be as follows. You would have a less than or equal to b, or z, a less than or equal to z, less than or equal to b. So a and z are bounded by constants. Okay, and then y has to be bounded by constant, but the constant now is in terms of this z, the first variable. And then the x needs to be bounded by constants, but now the constants are in terms of y and z. So this would be p of yz less than or equal to q of yz. Right? So you integrate with respect to x, which is bounded by variables, functions in terms of variable y and z. Y is bounded by functions of z, and z is bounded by constants. So that's how you would apply a more general type of region to this iterated integral. Okay, but let's draw the region in the ordering that I would normally do it. So here, let's say a and b are bounds for x. So x has constant bounds. And then the y is going to be bounded by functions of x. So this is g of x, and we'll say f of x, and this is g of x here. And so you have this region here. Let's make it a little more large. So you have this function g of x bounding on top, and the function f of x bounding below. And you've got this type of region. And then the z is caught between two variable functions. So you have the surface P of xy and the surface, well, this is right on the z-axis, cube xy. So I can move this over a little bit to make the drawing a little clearer. There we go. So that's A and B. On the x-axis, and then on the z-axis, or on the y-axis, you're bounded by f and g. And then on the z-axis, you're bounded by p and q, which are two variable functions. So you have a less than or equal to x less than or equal to b, fx less than or equal to y less than or equal to gx, and then pxy less than or equal to z less than or equal to qxy. So we don't say type 1, type 2, I mean, because there's actually 6 different ways to order such a thing. I'm not going to name them type 1 through type 6. But the first variable bounded by constants, the second variable bounded by functions of x, third variable bounded by functions of the first variable, and third variable bounded by functions of the first two variables. Okay, these types of integral regions, you can do an iterated integral over these types of regions, three-dimensional regions. Are 5 other ways to linearly order x, y, and z, and these yield together 6 types of regions. Of general 3D regions over which we can apply iterated integration. So, for example, consider the following region. So here's x-axis, y-axis, z-axis, and let's mark off 1 on each axis. So now consider this solid I'm about to draw. Okay, so what do we have here? On the top, this is the plane y plus z equal 1. The plane y plus z is equal to 1. And on the side here, this is the parabolic sheet y equals x squared. And right here is the point 1, 1, 0. And of course, this is the YZ plane that this sort of heel-shaped thing is butting up against. This region can actually be described for all for any of the 6 different orderings of x, y, z. It can be described in each way. I mean, not all regions are really special like this, but this one is. Okay, this 3D region can be described as above for all possible of x, y, z. Let's list all of them. Let's list all of them. Okay? So the easier ones, we'll do those first. First, we'll do y. Okay, this is 1 on the y-axis, 1 on the z-axis. Okay, and this is the plane y plus z is equal to 1. So y on the y-axis, right, what is the range on the y-axis? We're going from 0 on the y-axis to 1, right? Let's do that in, mark that out in red or orange. Right, y is going from 0 to 1. So 0 less than or equal to y less than or equal to 1. So now for any specific y, in the range from 0 to 1, z is going from 0, z equals 0, to z equals this. Z equals 0 to z equals what? Z equal to 1 minus y. Alright, so 0 is less than or equal to z is less than or equal to 1 minus y. Okay, but actually I don't want to leave those lines there because we're going to have to do this for all the other variables as well. So 0 less than or equal to y less than or equal to 1. 0 less than or equal to z less than or equal to 1 minus y. So now for any point in the yz plane, so imagine this orange dot is in this triangle of the yz plane. So let me move it over slightly, put it down here. Now extend it outward in the x direction, and where does it bump up against? It bumps up into this cylinder. That cylinder, y equals x squared. So x is going from x equals 0 to x equals square root y. X goes from 0 to square root y. Right, so we've got y bounded by constants, z bounded by functions of y, and x bounded by functions of y and z. I know the z doesn't appear there, but that's fine. Okay, it's bounded by functions of y and z, they just happen to not be using z. They happen to not depend on z. So that's yzx. How about zyx? Very similar. What about the z? Okay, z is going from, on the z-axis, z is going from 0 to 1. Now in the zy plane, if I pick a z, okay, so first we start on the z-axis. Z is going from 0 to 1. Now, if we stick to the yz plane, if you get a z right here, then the y is going from here, the z-axis, which is y equal to 0, to this right here, which is y equal to 1 minus z, right? Z goes from 0, or sorry, y goes from 0 to 1 minus z. Come on, there we go. So 0 less than or equal to z less than or equal to 1. 0 less than or equal to y less than or equal to 1 minus z. And then again, if you put a point yz in this triangle in the yz plane, then the x value goes from that yz plane, right, and that's x equal to 0, up to this parabolic cylinder, which is x equal to square root y. Same as before. So 0 less than or equal to x less than or equal to square root y. So z is bounded by constants, y is bounded by functions of z, x is bounded by functions of y and z. So this one's a little bit more sort of in line with our expectations because the z is here and the y is there. Of course, you could also have a z here, but you don't, but that's fine. What other ordering? Let's try x, y, z. What about x? So on the x-axis, x is going from where to where? X is going from 0 to 1 on the x-axis. Yeah, the solid doesn't touch that part. But whatever x coordinates you got, they're between 0 and 1, right? Or they're over here, or over here, or something like that. But at any rate, the x coordinates are between 0 and 1. So think of it as just on the x-axis. All right, so x goes from 0 to 1. Now, given a value on the x-axis, where's y? In the xy plane. Given a value for x between 0 and 1 on the x-axis, okay, in the xy plane, we're going to the next variable, xy. In the xy plane, y is caught between this and this. Well, what's that? That's y equals x squared, y equals 1. So 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal, x squared less than or equal to y less than or equal to 1. Oops, I didn't erase. All right, then what about the z? What about the z? So first we started with x and y. So if you imagine a point in the xy plane in that inside parabolic thing, then z is going from the xy plane up to, boom, this plane here, which is the plane, right, z equal to 1 minus y. So z goes from 0 to 1 minus y. 0, oops, less than or equal to z, less than or equal to 1 minus y. Nice. Next, let's try yxz. So y, just on the y-axis, y is going from 0 to 1. And then x is going from where to where? X is going from x equals 0 to x equals root y. Right? Y is going from 0 to 1 on the y-axis, and then x goes in the xy plane, goes from 0 to x equals root y. X equals 0 to x equals root y. And then z is going from the point in the xy plane up to this plane, z equal to 1 minus y. 0 less than or equal to z, less than or equal to 1 minus y. Okay, the last two are the harder ones. The last two are the harder ones because they start with x and z. So we're going to do zxy and then xzy. And those are going to be a little on the trickier side, but not really. So let's redraw here. If I was to take this like heel-shaped or half a cheese wedge-shaped region here, and I was to smoosh it in that direction, all right, I'm going to take it and flatten it straight that way into the xz plane. Okay, what do I get? What is the image that I get in the xz plane? All right, well, basically we need to know what the shadow of this edge here is in the xz plane. What is the shadow of this edge here in the xz plane? I mean, certainly we're going to get the entire x-axis from 0 to 1. Entire bit of the x-axis from 0 to 1. And the entire bit of the z-axis from 0 to 1. You're going to get that. But then there's going to be some sort of nebulous something or other going on there. Right, well, I've got this edge here is the intersection of the parabolic cylinder, y equals x squared, and the plane, so x is equal to y squared, and the plane, y plus z equal to, maybe I should have left those guys there. So y equals x squared. No, this is going to... So this is y equal to 1 minus z, this plane on the top. And then, of course, down in here, y equals x squared. Right, is that cylinder over there. So, y is equal to x squared, and then y is equal to 1 minus z. So I want to eliminate the y, right? I want to see what the shadow of this edge here is in the xz plane. Okay, well, the x squared is equal to y, and then the y is equal to 1 minus z. So this gives me the equation x squared equals y equals 1 minus z. Right, so I'm left with z equals 1 minus x squared. Right, so I'm left with this parabola right there in the xz plane. It certainly doesn't look like it. There we go. And I should do a different color there. Nice maroon color. Or brown color. So this is z equal to 1 minus x squared. And that, therefore, is the shadow, right, of this region when you smash it straight that way along the y-axis into the xz plane. Right, so that's z equal to 1 minus x squared, which is also given by x equals square root 1 minus z. So now we can write down the last two orderings. Okay, well, on the x-axis, x goes from 0 to 1. And then on the xz plane, right, x goes from 0 to 1. And then on the xz plane, z goes from 0 to 1 minus x squared. And then if you took a point here in the xz plane, where's the y? Well, y starts at this parabolic cylinder, y equals x squared, to y equals 1 minus z, right? From here to here. Y equals x squared to y equals 1 minus z. It doesn't start at the 0, right? That block is off the xz plane. So it's x squared less than or equal to y, less than or equal to 1 minus z. X squared less than or equal to y, less than or equal to 1 minus z. And now, right, it has all the variables appearing at each step. These the x is bounded by constants, the z is bounded by functions of x, and the y is bounded by functions of x and z. I mean, there's only x here and not z, and only z here and not x, but I mean, both variables do appear. And then if you wanted to do z first, 0 is less than or equal to x, less than or equal to z, or, sorry, 0 is less than or equal to z, less than or equal to 1. And then x goes from 0 to square root 1 minus z. Right, and x squared less than or equal to y, less than or equal to 1 minus z again. Right, z goes from 0 to 1. And then x goes from the z-axis, which is z equals 0, to z equals square root 1 minus x. And then the y goes from here to here again. Here to here. Okay, so that region has all 6 possible descriptions. Of course, not every region is going to, be as nice as this one, but there it is. Try this one for yourself. Very similar. Describe the region as above in 6 different ways. So I'm just going to change the idea of that region just a tiny bit. So blocking off one for each variable. So again, this is going to be, oh, it doesn't really look it. Let me try that again. Better. So this is going to be equal to y plus z equal to 1 on the top. That's the plane, y plus z equal to 1. And that's straight up and down like that. Nice and flat. And then here on the side, this is, again, the parabolic cylinder. Instead of x equal to y squared, it's going to be the parabolic cylinder. Instead of y equals x squared, it's going to be x equal to y squared. Okay, so very similar to this one. Instead of, being convex over here, it's concave. Okay. Now, how do you apply that to triple integrals? Well, probably you could have guessed this is going to be the case. Now, given a 3D region R equal to A less than or equal to X less than or equal to B, Fx less than or equal to Y less than or equal to Gx, and Pxy less than or equal to Z less than or equal to Qxy, the triple integral over the region of the continuous function fxyz dv is going to be the triple iterated integral where you integrate with respect to the bounds for P and Q, dz, right? When you're doing the antiderivative with regard to z, x and y are constants. So this is a constant, that's a constant. So that's appropriate, right? That's a constant, and you're holding, because you're holding y and z constant. And then the z disappears, and then you're just left with x's, right? And then you do your x's and y's. Then you do your integration with respect to y. You do your integration with respect to y, holding x as a constant. So that's a constant bound, and that's a constant bound. And then at the very end, you do your integration with regard to x with constant, and then the y's disappear after that step. Then you do your integration with respect to x from a to b. Right, and then that's done in the analogous fashion for the other 6 orderings. So let's calculate for that same region, this one here. Oops. So this is our region R. So let's calculate the triple integral over R, just z dv, in 2 different ways. Okay, we'll use this one first. And then we'll do the other one. Let's say xzy, where's that one? Okay, so we're going to do dz, dy, dx, and dy, dz, dx. So we're just switching the y and z around each time. Alright, so the triple integral of z dv over r is equal to the triple iterated integral from 0 to 1 minus y, x squared to 1, 0 to 1, z, then this is dz, dy, dx, dz, dy, dx. So first, antiderivative with regard to z. Antiderivative with regard to z is 1/2 z squared from z equals 0 to z equals 1 minus y, dy, dx. So this is equal to 0, 1, x squared to 1, 1/2 1 minus y squared, minus 0. Well, I'll leave that out. Dy dx. Okay, antiderivative with regard to y is going to be 1/6, negative 1/6, negative 1/6, 1 minus y to the third. Right, because the derivative of this is 3 times negative 1/6, which is 1/2. 1 minus y squared times negative 1, the chain rule, which gets rid of that, negative 1. And that's from y equals 0 to y equals 1, dx. So, or no, y equals x squared, excuse me, to y equals 1. So that's the integral from 0 to 1. At y equals 1, you get 0 minus becomes plus 1/6 1 minus x squared to the third dx. Unfortunately, we are going to have to multiply that one out. Yeah, unfortunately, we're going to have to multiply that out. So that's the integral from 0 to 1. Pull the 1/6 out here. 1 minus 3x squared plus 3x to the 4th minus x to the 6th, right? 1, 3, 3, 1 using Pascal's triangle, right? 1 to the 3rd, then 1 times negative x squared times 3, and then 1 times negative x squared squared, and then negative x squared to the 3rd dx. So this is equal to 1/6 x minus x to the 3rd plus 3/5 x to the 5th minus 1/7 x to the 7th from 0 to 1. So this is 1/6 1 minus, so that you just have to evaluate at 1 and then evaluating at 0, of course you get 0. 1 minus 1 plus 3/5 minus 1/7. And this is equal to 21 minus 5 is 16 over 35. So this becomes a 3, that becomes an 8, so you get 8 over 105. Okay? So that's the first calculation. So now we'll do the... Okay, so let's calculate again. The triple integral over r z dv is the triple iterated integral. So for this second region, there's a little mistake up here. I wrote 1 minus x. It's supposed to be 1 minus x squared, of course. I just wrote 1 minus x inadvertently. So it's 1 minus x squared here. So we have x squared to 1 minus z. 0 to 1 minus x squared, 0 to 1. Z, and then this is dy, dz, dx. Right, going from bottom to top, dy, dz, dx. Right through there, dy, dz, dx. Alright, so antiderivative with regard to y is just zy from y equals x squared to y equals 1 minus z, dz, dx. So evaluating at y equals 1 minus z, you have z times 1 minus z, and then evaluating as z squared, you have zx squared. dz dx. All right, let's clean up that expression a little bit. So I have z minus z squared. So I have z and z here. So it's z, well, let's write it out, z minus z squared minus zx squared dz dx. So let's rewrite that. So z times 1 minus x squared minus z squared dz dx. And antiderivative with regard to z, this x expression, of course, is constant. So I've got 1 half z squared, 1 minus x squared, minus 1/3 z to the third, from z equals 0 to z equals 1 minus x squared dx. Right? After the first round, by the way, right, we integrated with regard to y. All the y's went away, and we're just left with x's and z's. Now we're integrating with regard to z, and all the z's are going to go away, and we're just going to be left with x's. So we've got the integral from 0 to 1, 1 half. So 1 minus x squared times 1 minus x squared. And then at 0 you get 0 minus 1/3, 1 minus x squared to the third dx. This is 1 minus x squared to the third again. So this is equal to the integral from 0 to 1, 1 half, 1 minus x squared to the third, minus a third, 1 minus x squared to the third. So that's equal to a half minus a third is a sixth, 1 minus x squared to the third dx. Unfortunately, we can't do a u substitution. We're going to have to multiply it out. So that's 1 minus 3x squared plus 3x to the fourth minus x to the sixth. Antiderivative is 1/6. Is that the same integral we had last time? It is, right here. Right? Giving us that answer. So we don't need to redo that. Right? That was the same integral as before for x. Or dx as before. Alright, so that's equal to, so we know for sure that's equal to 8 over 105, same answer. Alright, so that's two calculations of the same integral. You can do it, of course, in 4 more ways, but we're not going to do all those. Okay, why don't we leave off, I think the lecture is long enough, we'll leave off here with that example, and we're going to do plenty of examples in class. So that's the end of the lecture on this section.